Eğer ki hayatımızda hiç eğer olmasaydı nasıl olurdu? Size şöyle söyleyeyim. Her şey daha az parlak, daha az yeşil olurdu ve daha az parlak yeşil. Çünkü eğerler ormanların derinliklerinde tek bir kibritle devrimlerin kıvılcımını ateşler. Eğerler Nobel ve Guggenheim'ın aklına takılır ve o kodu bu kodu çözerler. Eğerlerle içinizden haykırmak gelir. Eğerler bariyerleri kırarlar. Asla yalnız yürümezler ve aşırı bulaşıcıdırlar. Eğerler aşikardır ve son anda golü atarlar. Eğerler dünü umursamazlar, robotlarla bile konuşabilirler. Karşı takım soluklanırken oynamaya durmadan devam ederler. Sadece basit bir kelime öyle mi? Hayır. Eğerler asla uyumazlar, hep daha fazla çaba gösterirler. Eğerler bakar, araştırır ve en beklenmedik zamanda ortaya çıkarlar. Eğerler klonlanarak çoğalırlar. Acaba gerçekten yapabilir misin? Yaptın bile. Eğerler aklınıza girmeye çalışan güler yüzlü şakacılardır. Eğerler kapıları açarlar, asla kaybetmeyeceklerini bilirler. Ve biraz gün ışığına her zaman hazırdırlar. Her şey bir eğerle başlar. Çünkü eğerler ne zaman dönüşür, ne zamanlarsa şimdi. Ve şimdi nasıla dönüşür. Nasılsa asıl. Eğerler bakış açınızı değiştirir. Eğerler oyunu değiştirir. Eğerler dünyayı değiştirir. Biliyoruz. Çünkü biz eğerlerle çalışıyoruz. Yakın Doğu Üniversitesi.
Hello, dear colleagues. I am pleased to open the afternoon sessions of our international conference of new developments in soil mechanics and geotechnical engineering. We have valuable contributions, and there are 6 presenters. Each will be given 10 minutes. I would like to ask to the attendees to send their questions through the chat part on your screen. And at the end of all the presentations, there will be a 15 minutes time for discussion and with the presenters. We will start with Mr. Mindaugas Zakarka, and he will be presenting granular soil relationship between angle of internal friction and uniformity coefficient. Yes, Mr. Zakarka, please take the scene.
Thank you. My name is Mindaugas Zakarka. I'm a PhD student in Vilnius Gediminas Technical University. And as you heard before, the thesis of my presentation is granular soil relationship between angle of internal friction and uniformity coefficient. Why is it important? The idea of this is to determine physical and mechanical properties of the coarse soils, gravels, and the sands, which are used in road embankments. I found them in the exact objects in Lithuania. And to assess granular materials relationship between the mean particle size and the angle of internal friction, and also between coefficient of uniformity and the angle of internal friction. You can see in the photos how a specimen looks after the triaxial tests. So why it is important? I found that a lot of different researchers made to determine the relationship of particle size with angle of internal friction. For example, direct shear test, triaxial test, 2D and 3D discrete element method analysis. And conclusions were obtained you can see that at low sandy soil densities, the angle of internal friction decreases with increasing effective diameter of the particles. Sandy soils have a direct relationships between the angle of friction and the coefficient of uniformity. The grain size distribution can greatly affect shear strength characteristics in sandy soils. And the main conclusion is that the further investigations are needed. So I had 6 different soils. 3 of them are gravels and 3 of them are sands with a different. 2 of them is poorly graded gravels, 1 is medium graded, 2 poorly graded sand, and 1 medium graded sand. I found I conducted a proctor tests, standard proctor tests to determine optimal water content for to reach optimal density of the specimens, and I use them in the triaxial tests. Specimen of my specimens is diameter of 100 millimeters and height is 200. The conditions is unsaturated. That means that only optimal water content is added for preparations of the specimens and for compaction, and no more water is added. Consolidate all the samples consolidated for 30 minutes, and based on that, a vertical strain velocity was accepted, which is equal to 0.95% per minute, and the maximal deformation is equal to 15% was reached. It is important to select the right cell pressures for the triaxial test. And after analysis of 4 normative documents which are used in Lithuania and calculations, I found out that under the embankment, which are affected by traffic load, it is normal to expect cell pressures 20, 50, and 70 kilopascals. So 6 different soils and 3 different cell pressures. So after the triaxial test and other tests, I found out uniformity coefficients, the angle of internal frictions, which is most important for me. And I found out a few relationships. First one is the relationship between average size of particles in gravel soil and the angle of internal friction. When the average particle size increase, the angle of internal friction increase too. But I didn't find the relationship between coefficients of uniformity and angle of internal friction for gravel soils, and opposite for sandy soils. When the coefficient of uniformity increase, the angle of internal friction increase, and there was no relationship between the average particle size of sand and the angle of internal friction. So increasing the coefficient of uniformity in sandy soils decreases the angle of internal friction. it doesn't work for gravel soils. For gravel soils, increasing the average particle size increases the angle of internal friction. And the main conclusion is that there is the relationship between the particle size distribution and the angle of internal friction, but the results is still debatable. So thank you.
Zakarka, and thank you very much for just being on time. And now we will continue with the second presenter. Excuse me. Yes, we will continue with clay soil stabilization using Santan gum and sodium alginate as biopolymers. And the presenter is Ayberk Temurayak. The paper was written by Ayberk Temurayak and Tuğba Eskişar. Mr. Temurayak, could you please start your presentation?
Hear me? Can you hear me?
Yes.
Dear audience, my name is... Can you see the screen?
Thank you. It's okay.
Dear audience, my name is Ayberk Temurayak. I am MSc student in Ege University, Turkey. The title of my presentation is Clay Soil Stabilization using Xanthan gum and sodium alginate as biopolymers. It is well known that stabilization with cement or lime is highly popular around the world. However, the carbon dioxide emission of cement has raised the necessity of environmental friendly additives. One of them is biopolymers. Biopolymers are polymers produced by living organisms. Molecules such as cellulose, starch, chitin, proteins, peptides, DNA, and RNA can be given as an example. These biopolymers are composed of monomers called sugars, amino acids, and nucleotides, respectively. Apart from these biopolymers, which are widely found in nature, there are also products that are used in the food industry, especially in terms of thickeners. Some of these biopolymers are xanthan gum, guar gum, chitosan, sodium alginate, and locust bean gum. Studies conducted in recent years have shown that these biopolymers used in the food industry can improve the properties of soils, such as compaction, compression, and strength, by using them in different soil types such as sand, clay, and silt. Recent investigations have proposed the use of biopolymers which facilitate the direct application in the field for problematic soils to improve their engineering properties. In this study, two types of biopolymers, xanthan gum and sodium alginate, were used. Xanthan gum is a polysaccharide obtained from the fermentation of glucose or sucrose with Xanthomonas campestris bacteria. It is used as a stabilizer and thickener additive in food industry. It has high thickening properties even in low amounts, like 0.5% and 1%. And the sodium alginate is the sodium salt of alginic acid, the main source of which is brown algae. It is used in the food industry because it prevents the spoilage of foods and provides a gel consistency. It is beneficial to increase the plasticity of materials such as cement, plaster, and mortar. Due to these features, the variation of studies on soil stabilization using different biopolymers are increased recently. Since the beneficial effect of biopolymers is evident in fine-grained soils in the literature, kaolin clay was used in this study. The wet mixing method was used in the preparation of the samples in all tests. According to this method, biopolymers were prepared as a solution first and mixed with water with the weight of water, mixed with soil by weight of water. Biopolymers used in the soil stabilization were generally mixed with soil at rates ranging from 0.25% and to 4%, as they have a high consistency increase feature even at low concentrations. The ratios that give the best results may vary depending on the parameters investigated. For example, while 1% concentration gives the best results in the consolidation test, 2% concentration can be the optimum value for unconfined compressive strength. Therefore, the biopolymer ratios should be determined according to the soil feature that stands out in the project. In this study, determined xanthan gum ratios were from 0.5% to 3%, and sodium alginate ratios were from 1% to 4%. In this study, Atterberg limits tests, standard Proctor tests, unconfined compression tests were performed for determined biopolymer concentrations to evaluate the geotechnical properties of treated samples. Compaction tests were carried out to determine the optimum water content and maximum dry unit weight of clay and biopolymer treated clay. The unconfined compression test samples were prepared at their corresponding optimum water contents and compacted under a standard Proctor energy, which is 600 kJ per cubic meter. After compaction, samples were extracted from the mold with the help of a jack and subjected to air curing for 7, 28, and 56 days. When the curing stage was completed, the samples were subjected to the unconfined compression test.
Excuse me, there's a problem with the slides. The slides are not changing. If possible, could you go through from the beginning?
Okay.
In a fast way, quickly, please.
En baştan.
Mhm.
En baştan.
Yes, yes, please.
Dear audience, my name
And
is
could
Ayberk
you make
Demirel.
it full screen? Full screen, could you make it?
Dear audience, my name is Ayberk Demirel. There's a problem with full screen in my computer.
Okay. It's okay now. Let's continue from the second slide. We followed this one. Yes.
It is well known that stabilization with cement or lime is highly popular around the world. However, the carbon dioxide emission of cement has raised the necessity of environmentally friendly additives. One of them is biopolymers. Biopolymers are polymers produced by living organisms. Molecules such as cellulose, starch, chitin, proteins, peptides, DNA, and RNA can be given as an example. These biopolymers are composed of monomers called sugars, amino acids, and nucleotides, respectively. Apart from these biopolymers, which are widely found in nature, there are also products that are used in the food industry, especially in terms of thickeners. Some of these biopolymers are xanthan gum, guar gum, sodium alginate, locust bean gum, and chitosan, etc. Studies conducted in recent years have shown that these biopolymers used in the food industry can improve the properties of soils such as compaction, compression, and strength by using them in different soil types such as sand, clay, and silt. Recent investigations have proposed the use of biopolymers which facilitate the direct application in the field for problematic soils to improve their engineering properties. In this study, two types of biopolymers, xanthan gum and sodium alginate, were used. Xanthan gum is a polysaccharide obtained from the fermentation of glucose or sucrose with Xanthomonas campestris bacteria. It is used as a stabilizer and thickener additive in the food industry. It has high thickening properties even in low amounts, like 0.5% and 1%. Sodium alginate is the sodium salt of alginic acid, the main source of which is brown algae. It is used in the food industry because it prevents the spoilage of foods and provides a gel consistency. It is beneficial to increase the plasticity of materials such as cement, plaster, and mortar. Due to these features, the variation of studies on soil stabilization using different biopolymers is increased recently. Since the beneficial effect of biopolymers is evident in fine-grained soils in the literature, kaolin clay was used in this study. The wet mixing method was used in the preparation of samples in all tests. According to this method, biopolymers were prepared as a solution in water and mixed with soil by weight of water. Biopolymers used in the soil stabilization were generally mixed with soil at rates ranging from 0.25% to 4%, as they have a high consistency increase feature even at low concentrations. The ratios that give the best results may vary depending on the parameters investigated. For example, while 1% concentration gives the best results in the consolidation test, 2% concentration can be the optimum value for unconfined compressive strength. Therefore, the biopolymer ratios should be determined according to the soil feature that stands out in the project. In this study, determined xanthan gum ratios were from 0.5% to 3%, and sodium alginate ratios were from 1% to 4%. In this study, Atterberg limits tests, standard Proctor tests, unconfined compression tests were performed for determined biopolymer concentrations to evaluate the geotechnical properties of treated samples. Compaction tests were carried out to determine the optimum water content and maximum dry unit weight of clay and biopolymer treated clay. The unconfined compression test samples were prepared at their corresponding optimum water contents and compacted under a standard Proctor energy, which is 600 kJ per cubic meter. After compaction, samples were extracted from the mold with the help of a jack and subjected to air curing for 7, 28, and 56 days. When the curing stage was completed, the samples were subjected to the unconfined compression test and the stress-strain variations were recorded. The liquid and plastic limits of the kaolin clay was determined according to ASTM standard. The liquid limit of the clay was 51.3 and plastic limit was 36.5 and the plasticity index was 14.8. The optimum water content of the clay was 31% and the maximum dry unit weight was 1.64 tons per cubic meter. Considering the results of the liquid limit tests, a significant increase observed on treated samples. While the liquid limit increased by 34% with the addition of xanthan gum from 51.3 to 68.7, an increase over 100% from 51.3 to 133 with the addition of sodium alginate. At the highest concentration of sodium alginate, the rapid change in viscosity leads to a nonlinear increase in the liquid limit. Plastic limit increased with the addition of biopolymers, but compared to the liquid limit, the increase of the plastic limit was very low, which is only 1%. Since the liquid limit increased more than the plastic limit, the plasticity index was also increased. Adding water to the biopolymer-treated soils activated the monomers of the biopolymer and formed ionic and covalent bonds with soil particles. Thus, monomers required more water, which increased the liquid limit and plasticity index of the soil. In this figure, the blue curve represents the xanthan treated sample, and the green curve is sodium alginate treated sample. As a result of the compaction test, the optimum water content of kaolin clay was 31% and maximum dry unit weight was 1.64 tons per cubic meter. With the addition of 2% xanthan gum and the 3% sodium alginate, the optimum water content increased by 3% and reached 34% with both biopolymers. The maximum dry unit weight was decreased slightly and reached 1.6 tons per cubic meter in xanthan treated sample, and also decreased slightly and reached 1.56 tons per cubic meter in sodium alginate treated sample. The decrease in the maximum dry unit weight and the increase in the optimum water content was due to the fact that the monomers located in the pores between the soil particles absorb more water and cause a net decrease in particle interaction. The unconfined compressive strength of untreated clay was 280 kPa. The strength of the treated samples improved with increasing biopolymer ratio and curing time. While the increase of the unconfined compressive strength was 2.6 times in 56-day cured samples treated with 2% xanthan gum, which is 733 kPa, and the increase was 3.8 times in 56-day cured samples treated with 3% sodium alginate, which is 1017 kPa. As a result, optimum xanthan gum and sodium alginate contents to be used for treatment were found to be 2% and 3% respectively. In this study, two types of biopolymers were used as an alternative soil stabilizer. Atterberg limits, compaction, and unconfined compression tests were performed with the determined concentrations of xanthan gum and sodium alginate. The liquid limit increased in all treated samples, and they were higher in sodium alginate treated samples compared to xanthan gum treated samples. Plastic limits increased in both xanthan gum and sodium alginate treated samples, and also plasticity index increased in both treated sample groups. The optimum water content increased by 3%, and maximum dry unit weight of the treated samples decreased, and the lowest MDD was achieved in sodium alginate treated samples. The UCS of the treated samples improved at optimum biopolymer ratios and with curing time. As a conclusion, soil stabilization with biopolymer additives is a promising approach in geotechnical applications. Thank you for listening.
Thank you, Mr. Ayberk Temurayak. And I would like to see if there are any questions. Not yet. I would like to remind the attendees, if they have any questions, they can write it on the chat box on the right-hand side of the screen. Thank you, and I will continue with the third presentation, that is apparatus design and measuring of apparent swelling pressure of compacted bentonite. The lecture will be delivered by Hailong Wang, Takumi Shirakawabe, and Daichi Ito are the authors of the paper. But yes, Hailong Wang is in the studio to present his contribution. Thank you. Please, Mr. Wang.
Thank you. Is it possible to see the screen? Hello.
Yes, it is.
Can you see the screen? Is that okay?
Yes, it seems okay.
Okay, great. Thank you.
Thank you.
Let me start my presentation. I'm Hailong Wang from Waseda University here in Japan. Right now it's evening. I would like to talk about the apparatus, the design of the apparatus in order to measure so-called apparent swelling pressure of compacted bentonite. Oh. Okay. I think this study is kind of not so familiar with the audience. I would like to introduce the background. One of our studies focusing on the geological disposal in order to deal with the high-level radioactive waste from the energy system. So the idea of this system is to put the radioactive waste deep in the ground, like several hundred meters in the ground, and here the waste itself, and it was protected or isolated by several bearings. Like this is the steel container, and outside is the so-called buffer material, and outside this buffer material is bedrock. The bentonite I'm talking about today is related to this buffer material. So bentonite was used as a main material for this buffer material. Buffer material as shown here. It's a compacted condition like this condition, and after absorbing water from underground, as you may know that the volume of the bentonite will swell like this, because in the disposal condition, the swelling deformation was confined by the bedrock. So basically, instead of swelling deformation, there's some pressure generated in the underground condition. So I called this pressure as apparent swelling pressure. This is a pressure we are trying to measure in this study. So the objective of this study to design an apparatus to measure this apparent swelling pressure PS, and to develop a method to measure it accurately. Okay. To measure the swelling pressure, of course, in the past there are many studies. Basically, they use the consolidation apparatus in the past often. There are several ways. For example, one way is first to saturate the specimen without any confining condition to allow the free swelling. And then after the saturation, we apply the load in the consolidation apparatus, apply load step by step until we found the volume return to the original volume. So we put this pressure as the apparent swelling pressure. This is the one way. Another way would be we prepare different specimens, and for different specimen we apply different initial load. For example, this one would be 0, some load, and under the initial load we saturate the specimen, and because of course under the higher load the deformation will be small, and we can find some point that corresponding to the 0 deformation. So we define this point as the swelling pressure. This is a second way. A third way would be we try to keep the volume as constant as much as possible. When we find some deformation, we immediately apply the load to return the deformation. And during the saturation, if the deformation happen again, swelling happen again, we apply another load. So gradually, as the load increase, there will be a point that there will be no more load anymore after the saturation. So at this point, we can define another pressure as swelling pressure. This is the third way. And last way is different from the last three ways. We kind of design a different apparatus. In this apparator, we use the rigid confining wall to initially confining the deformation, swelling deformation. So we basically confining this deformation and swelling saturated the specimen until the full saturation. And after saturation, we get one pressure. We can measure one pressure from the from many ways. Okay. For this, all of the 4 ways, basically recently for the compacted bentonite, usually the third way and fourth way are very popular. But one question is, it's not that easy to measure very accurate swelling pressure. For example, this is a so-called the final equilibrium swelling pressure, and this is the dry density. You can see even under the same dry density, the data is scattering very much. This is a so-called calcium type bentonite, and for sodium bentonite also under the same dry density, even the same experimenter, the data is very skeletal. So we're considering how to get a good testing method to in order to measure this pressure. Then we developed this apparatus as shown here. Here is the specimen here. The size is a diameter of 26 millimeter and height is 10 millimeter. Compared to the consolidation test, the size is very small. This is because the bentonite, it takes a very long time for saturation. We try to reduce the size of the specimen. And this is a specimen, and here's the loading plate. Under this loading plate, there's a load cell and a bearing, and here's the screw. Okay, so before the test, we prepare a specimen in this motor ring, and we rotate this screw so that the load cell and the loading plate slightly go upper in order to confine the deformation. I mean, it's not directly, this load is not directly applied on the specimen because this diameter, the load plate diameter, is slightly larger than the specimen diameter. So actually, it would be directly applied on the motor ring. We apply an initial confining pressure. And then we apply water from here, okay, from here. Later, we explain in the detail from here, then the water can transport it into the specimen, and air can escape from this path. Okay. Like here's a detail of the water path. Here there is a small gap, so the water can transport from this small gap and go through the specimen through one mesh at the bottom. This is a mesh, and at the top here is filter paper. So water goes through the specimen through these 2 layers. We didn't use the porous metal that usually used, for example, porous metal, porous stone. We didn't use this kind of material because in order to set up this this part, it's easy to cause some gap like here, and basically the material itself it's soft compared to the steel. So in order to reduce the specimen deformation, we select this mesh and filter paper combination. And of course, for the mesh, we try to reduce the pore size. For example, we used a very thin and small size mesh compared to the traditional porous metal. The pore is very small. And in order to confirm this system works well, we conduct 2 tests. For one test is use the porous metal. The vertical axis is the inflow of water. So the amount of water applied supplied to the apparatus. And another, this red one is the current system. Okay, this water is not all flow into the specimen because there's some space in the water flow path. Okay, we try to estimate the water path space. We minus this space and get the water that actually inflow to the specimen. As you can see, this two curve with traditional way and calendar way is very similar. Of course, we conduct some other tests to confirm this method. Basically, it's quite reliable to transport the water. However, because we used the filter paper is also compressible, have some deformation. If possible, we try to remove the filter paper, but if we remove the filter paper, it's not easy to transport the water into the specimen. So basically, we use the mesh plus filter paper system to conduct the test. There are some problems when we conduct the test. For example, because of the filter paper compression problem, sometimes we found that due to the sweating, some material, some bentonite squeezed out, like here, squeezed out. So for this problems, we try to refine the apparatus to increase the manufacturer accuracy to remove this kind of a problem. Another thing is the filter paper softening. It's different from the filter paper compression. So when we apply a filter paper under the specimen, the stiffness of the filter paper will reduce because of the water. Once the filter paper absorbs the water, it will becomes soft. So if we apply an initial load here, because of the deformation, softening of the filter paper, there will be a reduction of the stress. So this is another problem. But in order to distinguish where is the load applied initially and where is the swelling pressure we measured, we try to understand this way. We try to understand this pressure by applying some calibration test. In the test, we apply some air pressure to simulate the swelling pressure and apply the load. As a result, we can find that if we apply a relatively small initial load here, so basically when the pressure measured exceeded the initial pressure, the result will be the swelling pressure for the tested specimen. So to verify the apparatus, we used a bentonite, so-called Koeniger V1. Here is the basic physical conditions of this soil. So we prepared some tests, identical test. The first one, quite two very similar specimen. We apply the same initial load here, and during the water absorption, we measure the change of the load or the change of the swelling pressure. This is a very typical swelling pressure curve. So it's increase first and go down and go up until the equilibrium swelling pressure. Okay, this is very typical. However, when we try to change the initially applied load, it can be seen the measured swelling pressure also changes somehow. The larger the initial pressure we applied, the final swelling pressure we measured would be larger. So here's a problem. The problem is induced mainly because of somehow the initial pressure applied to the specimen. It's sorry, it's it's um a little bit complicated to explain here, but we found a way to solve it. So when we prepare a specimen, after the compaction of the specimen, we try to trim the surface of the specimen because of the deformation of the filter paper. There's some specimen outside of the range, so we try to trim this way and return the specimen so that before the test, there's a small space under the load cell. So by this way, we again prepared several specimen, the identical specimen, and apply the different vertical loading. As you can see, although from here there's still some very tiny difference, but basically compared to previous study, the results is quite similar. This is conducted by the same experimenter. In order to see any difference based on the experimenters, we conduct 3 tests by one experimenter and another 3 tests by another one. As you can see, for the same dry density, the measured curve is very similar, although there's some difference, but basically they're quite similar. And for different dry density, you can see the measurement is also quite well. As increase of the dry density, the pressure increase. Based on this technology, we also recently developed even smaller sized apparatus. So the specimen size, the specimen thickness reduced to 2 millimeter. Even with the 2 millimeter, as you can see, the relationship of dry density and the pressure are very unique. I mean, the skeletal terrain is very small compared to the past study. As a conclusion, we proposed apparatus and the test procedure to measure the apparent swelling pressure. And the reliability, I think, is very high with the proposed procedure. And the design drawing and the swelling and the specimen preparation method are open right now. So if you're interested in, you can check. Thank you very much. This is all from me.
Thank you, Mr. Wang. That was an excellent presentation and excellent paper.
Thank you.
I congratulate you for everything. I think you have
Thank you very much.
taken care of every concern, every detail. But if there are anything that our attendees might have seen or would like to contribute, we will be glad if they write through the chat box. Thank you very much. And we will continue with our next presenter. Effect of pre-drying inconsistency limits of soft plastic marine clays. And here, a group of authors, Guillaume Massale, Puig, sorry for the wrong pronunciation, Juan Marc Colomer Lorenzo, Alexandre Vancels Mora, and Amadeo de Lozano. And may I ask the one who will present this paper, and I would also like to ask them, although I forgot at the beginning, to present themselves. Okay, I think they are not here. Then we will continue it. Prediction of pressure meter parameter of cohesive soils using a machine learning model. Miriam Latif, Nureddin Mezouar, and Ramdan Bahar. Are they here? And I think we can continue with estimation of over-consolidation ratio and compression index by different methods, by F. Zishan, Padmavati, and Madhav. Please. Could you unmute your camera? We cannot see you. Ah, yes. Firdevs Zishan, yes. Could you please start your presentation?
Are my slides visible, please?
Yes, please, Mrs. Firdevs Zishan, please start.
Are my slides
Is there a
visible?
problem? Sorry,
Are my slides visible?
you are visible, but your slides are not.
Okay.
Could you share your slides?
Now,
Yes, it's okay.
hello everyone. I am Zishan Firdos, a student pursuing Masters in Geotechnical Engineering from Jawaharlal Nehru Technological University, Hyderabad. My co-authors are Professor Padmavati and Professor Madhav. My study is on estimation of overconsolidation ratio and compression index from different methods. The contents of my presentation go like introduction, methodology, source of data, results and interpretation, and then followed by conclusions. Introduction. Oedometer test is usually used to represent the one-dimensional soil deformation behavior plotted on a semi-logarithmic graph with void ratio versus effective stress. The pre-consolidation stress is an important parameter which plays a vital role in estimation of settlements, and also compression index also plays a greater role in estimation of settlements. Hence this study involves interpretation of pre-consolidation stress from different methods, and the analysis goes on. The methods used for interpretation of pre-consolidation stress are Casagrande method, Silva, Smirtman, Nagaraj et al. These are semi-logarithmic methods. Butterfield, Oikawa, Sridharan, these are bilogarithmic methods. Yanbu's method utilizes the concept of constraint modulus, in which soil deformation behavior is studied in only one direction. The most commonly used method is Casagrande method. This method This method utilizes the concept of maximum point of curvature. At this point, the tangential line and a horizontal are drawn, and the backward extension of virgin compression line intersects the line of bisection at point T. The stress corresponding to point T is pre-consolidation stress. Similarly, in Silva method, the backward extension of virgin compression curve intersects the initial void ratio line at point C, and the drop of a vertical from point C intersects the curve at point E. The extension of point E to the point F intersects the virgin compression line. The stress corresponding to point F is the pre-consolidation stress from Silva method. The Nagaraj method, from this method, the pre-consolidation stress is estimated from the intersection of normal drawn from point of maximum curvature, which intersects initial void ratio line at point D. The stress corresponding to this point D is pre-consolidation stress. The Smudman method is generally utilized in obtaining field compression curve. The backward extension of virgin compression curve from point 4 E naught to the initial void ratio line intersects at point G. A line EF is drawn parallel to the recompression curve, and the stress corresponding to the point F gives a pre-consolidation stress. Oikawa and Butterfield methods both are bilogarithmic methods. The linear portions of the curves are intersected at points A, and the stress corresponding to the points A are point A gives the pre-consolidation stress. Sridharan method is also a bilogarithmic method on which void ratio and effective stresses are plotted on both on logarithmic scales. The intersection of linear portion of the curves give sigma c, and Enbu's method utilizes the constraint modulus. When a significant drop in constraint modulus is observed, the stress corresponding to the point of drop gives the pre-consolidation stress. The compression index is calculated from the equations 1, 2, and 3. The equation 1 is a general equation which is the slope of E log sigma plot, which gives Cc. The compression index from Butterfield and Oikawa method is derived as the equation Cc is equal to Cc dash minus 0.0192 by 0.19, where Cc dash is the slope of the virgin compression curves from these methods. And the Sridharan method, the equation is derived as Cc is equal to Cc double dash minus 0.1067 by 0.23, where Cc double dash is the slope of log E versus log sigma plot. In this study, the data is collected from the sources which are already available in the literature. The site locations are from Egypt, California, and Kerala. After the analysis of the data, the obtained results can be presented as given here. The variation of the OCR obtained from various methods from that of Casagrande method are studied and tabulated. The variation from Silva method and Sridharan method is minimum. The range of variation is minimum for these two methods, Silva and Sridharan method. And similarly, the variation of compression index from that of Casagrande method is also tabulated. The CC obtained from Silva and Oikawa method, the range of variation is minimum, while the range of variation obtained from Sridharan method is maximum. From this entire study, we can infer that the only Casagrande method is not desirable to give the sigma c values in estimation of settlements. The results obtained from various methods can be analyzed, and the most repetitive results can be chosen to get appropriate settlement estimations. The conclusions of this study are the variations are higher at higher sigma c and higher overconsolidation ratios, as the sample has to undergo large range of unloading and loading cycles, and due to this there might be a variation in the estimated values. Butterfield, Oikawa, Sridharan methods, these are bilogarithmic methods, and the results obtained from these methods are most comparable, simple, and quick. The Nagraj and Smartman methods, the results obtained from these two methods can be utilized in depicting the true in situ behavior of the soil. Yangu's method gives the results which vary on a large scale. Thank you. This is all for my presentation. These are some of the references which I have used.
For this presentation, and now we will continue with volume change behavior of natural sands with the addition of mica particle. The presentation will be given by Furkan Egemen Kahya, and the co-author of the paper is Professor Tuğba Eskişar. Please, Furkan, can we listen you?
Hello. Okay. Good afternoon, dear listeners. This is Furkan Egemen Kahya. I'm Master of Science student at Ege University, and the topic of my presentation, volume change behavior of natural sand with the addition of mica particles. Why is the volume change behavior of the soil important? The volume change behavior determines the settlements due to compression, heave due to expansion, and it contributes to the deformations caused by the shear stresses. Interestingly, this phenomenon has been recognized in the ancient ages. For instance, archaeological excavation of ancient city of Mendes show that special type of foundation made up with fine sand layer and limestone block pavement was used to support the structures. Figures on the right side were taken from excavation site Mendes City. When we look over the literature, clays and clean sands have been studied extensively in terms of volume change behavior. Thereby, it becomes important to understand volume change behavior of natural sands with different percentages of fines. In this study, two different natural sands named Nazarköy and Yamanlar sands and fine natural mica were used to evaluate the volume change behavior and its effect on the shear strength of the soil. Nazarköy samples was taken from the Kemalpaşa district. On the other hand, Yamanlar sand was taken from near the Çiğli district. Also, natural mica particles were provided from a private company. According to ASTM standards, Nazarköy and Yamanlar samples both are classified as poor graded sands. Also, maximum void ratio, minimum void ratio, and specific gravities are given in the table. Within the context of this study, odometer test and triaxial tests were conducted. The grain sizes of both sands were limited between number 10 to number 40 sieves. For odometer test, natural state, and 7 different sand-mica mixtures were prepared under fully saturated state, and the sands were placed in the mold layer by layer with a smooth tamping technique. Incremental loading were applied in 9 stages, 12.5 kilopascal to 3.2 megapascal, and each loading stage applied 1 hour after end of the primary settlement, according to the method of ASTM standards. Triaxial tests were conducted on natural 10%, 30%, and 50% mica added sands in 4 stages. Samples were placed in 5 layers, and each layer was tamped down using a rod to maintain a relative density of 55% to 65%, and 3 different effective stresses were chosen as 50 kilopascal to 200 kilopascal. When a load was applied on the granular soil, the particles transmit the loads each other by the contact points of grains. This transmission creates a fictive force chain in the granular medium. Global void ratio is used to represent the mechanical properties of granular medium. However, when soil contains fines, another definition of void ratio become necessary. Therefore, intergranular void ratio concept is the approach to understand fines effect on the granular medium. It is basically void ratio of the granular part of the soil, and it is assumed to equal to the maximum void ratio. Hence, the mechanical response of sand with fines can explain in 3 different situations. First one, at lowest fine content, fine particles are in the voids created by grains, and coarse grains control the main behavior of soil. Second one, fine content is increased. They affect the force chain, and here both fine and coarse grains control the behavior. After this point, there is a threshold fine content that fine parts takes the control of soil behavior. And finally, third one, at highest fine content, fines fill the voids and break apart each contact point, and fines control to the behavior. In this study, Tevanyangam's intergranular void ratio equation was preferred. Threshold fine content can be found on intergranular void ratio to effective stress plane as the fine content where the compression curve converges to the maximum void ratio line. Threshold fines content of Nazarköy and Yaman-Larsens correspond to 12.5% and 17.5% mica percentages. Also, as a different perspective, if the fine content that shifts the soil behavior from granular part of the soil to fine part of the soil considered as a function of effective stress, it defines transition fine content zone. Starting from this point, Nazarköy samples show transition zone from 12.5% to 35% mica content. As for Yamanlar samples, they show transition zone from 17.5% to 39 mica content. Also, initial values of 12.5% and 17.5% mica supports the threshold content in the graph on the previous slide. The volume changes in sand exerted by fines content are not only important in terms of compressibility, they are also important in terms of shear strength. Because any volume change in the soil makes a contribution to the shear stress. Therefore, it is important to understand the fines content effects on the shear strength. If we look through the stress strain curves of samples with this standpoint, Nazarköy sands shear strength decreases with increase in mica content. Besides that, it shows a little increment at the 50% mica content, but it is still lower than its natural form. On the other side, the shear strength of Yaman-Larsen increase at 10% mica content, in contrast to Nazarköy sand. However, the shear strength of the Yamanlar samples decrease with increasing mica content. The maximum shear strength of these two sands were found at different mica contents. The reason for this is the median grain size differences of the two sands. This study aimed to investigate the effects of mica content in terms of volume change behavior and how it affects the shear strength response. In this sense, the results of this experimental study can be summarized as volume change and shear strength behavior of natural sand are directly affected by fines content. The mica affects the interparticle frictional mechanism of the granular medium. There is a certain fines content, so-called threshold or transition fine content, that shifts the soil's behavior from granular part of the soil to fine part of the soil, specific to the sand type. Within the experimental study, these threshold values of Nazarköy and Yamanlar sands are found as 12.5% and 17.5% respectively. Median grain size is one of the most critical parameters to determine the fines content where peak shear strength is observed. Median grain size of Nazarköy and Yamanlar sands are found as 0.30 millimeter and 0.92 millimeter. The peak shear strength of Nazarköy sand is observed in its natural state. However, the peak shear strength of Yamanlar sand is achieved at 10% mica content. As a further study, for better understanding of the engineering properties of natural sands with fines, mineralogical compositions of grains should be determined and their relationship should be investigated with image processing techniques. Thank you.
Mr. Furkan Egemen Kahya. This was really an interesting research work, and Your presentation was also very good. Thank you very much. And I think there seems to be no problems from no questions from the audience. Then may I start with you to ask some questions on some issues which I would like to learn. For example, may I ask to Furkan? I might have missed, but I just would like to learn. Did you find the void ratios, intergranular void ratios between fine content, within the finer part and also coarser void ratios? Did you have any idea about the size of the voids? Because I saw there was a block diagram.
Yes.
On that,
Yes.
it was written void ratio, but it was defined in terms of.
It was actually Tevanyangam's explanations of intergranular void ratio, and I want to use it to explain how it works.
Yes, is it fine content or is it related to the, or is there any classification between finer voids and or
Of course,
coarser?
there is a classification finer and coarser, but we use intergranular void ratio. It's also mean coarse part of the soil's void ratio. So we use coarser part of the void ratios.
Or did you find the average value as we always do during the laboratory test? For example, in consolidation test, did you just calculate the average void ratio, or did you make different calculations?
First of all, we calculate the maximum void ratios and average void ratios also. Yes, actually global void ratios.
Yes, that's what I meant.
After that, we convert at the intergranular void ratios.
Thank you. And did you make any interpretation related to, you mentioned about two types of soils, Yamanlar. Now I couldn't remember the other one.
Yamanlar.
In one of them with 10% of mica,
yes,
there was a better strength property.
Yes.
In the other one with 0%.
Yes.
Do you have any interpretation related to that one?
It caused because of the medium grain size differences. Because Yamanlar sands have larger in medium grain sizes, and the fines when we add the fines plays in the granular voids passively, but it creates better packing in
Thank you. Yes.
Granular medium.
Thank you very much. And I would like to ask to Mr. Zakarka. I think he is not here anymore. And may I also ask, or I would like to learn some other points. May I ask to Ayberk Temurayak? Ayberk, I would like to learn about how you treated the soils with the biomaterials that you used. Is there a method, or are those methods applicable in the field? What would be the results in the field? Of course, we are at the earlier stages of this research, I guess.
Uh, it is, yes, applicable.
In the field. And do you
field?
do you have an idea about the depth of infiltration of these additional materials in case of field work?
No. The
Yes.
late strength.
These are very new methods and new applications. That's why I would like to ask.
Sorry.
These are new methods and new applications.
Yes. Evet.
In geotechnical engineering. That is why I wanted to learn. Now I think you are, is it correct if I say that, you are now learning the response of these soils at laboratory scale, I think. Are you planning to continue in the field scale?
Yes.
Are you a master's degree student or PhD?
Master degree.
Master's degree. Oh, then that should be okay with you. Maybe afterwards, after you finish your master's degree. Anyway, thank you very much for this interesting study. And may I ask Zishan a question? Firdoshi Zishan. Okay, she has gone also. And I think we have to close the session if there is no one else. We have to close the session at this stage. And our next session will start at 15:45. Thank you for listening. Thank you for attending the session. And thanks to all of the contributors.
Catching a buzz, never nothing when it's real.